Okay, things are going to get a little bit more difficult here, so please make sure that you've really spent some time on the previous sections. So first thing I wanted to do is cover this question from the book. So what do you do if you can't really see the moment? Okay, so here's a good example where sometimes you need to extend the line of the force. 4,000, this was halfway up, so it was 30. Okay, it's much easier to see now that that is a clockwise moment at 30 times 4,000 n. Okay, this even applies for this diagonal one here too, for example. If you go like this, there's lots of ways you can then do it. You could say if that's 50, that's 50, and you could work out your distance that you then multiply by 6,000. Okay, so if you do get really stuck with some of these harder questions, extending the force line is a good way to do it. Right, we've covered up to now uniform rods. Uniform rods are when the mass is equally distributed, so we put the center of mass in the center. In other words, we found the middle of the object and the force went straight down. Well, it's not always like that, okay? If we are told that we have a non-uniform rod, then we're not allowed to assume that. So whereas before we would have said, oh, assuming it's 10 kilograms, 10g in the middle, we can't do that anymore. We still do that, but we say, I don't know where the 10g is. So the 10g is like an unknown distance, okay, from one end of the rod. That's the difference. Whereas before, if it were 5 meters, we would have said, aha, it's 2.5. We just can't do that anymore. We call it x. Apart from that, everything's the same. That really is it. So you need to read carefully for non-uniform rods. Sam and Tamsin are sitting on a non-uniform plank, AB, of mass 25 grams and length 4. So although it's tempting to say it's 2, the center mass is 2 in, we don't know that. We still know how long the plank is, but we don't know where the center of mass is. The plank is pivoted at M, which is the midpoint. Okay, so we're starting to build a bit of an image here. So this is M, the midpoint of AB. The center of mass is at C, and AC, oh, they have actually told us where it is. AC is 1.8. Well, if the whole thing is 4 meters, 1.8 is going to be slightly to the left. So it's going to be there, something like that. AC. So mass 25 kilograms, so that's 25g. So I actually, and on this occasion, we do know where it is, but the key idea is it's not in the middle. If that's 0.2, that's 1.8 then. AC is 1.8. I'm tempted to do that. Let's just see. I'll put that down for now. So non-uniform, I suppose we've done that already. The length is 4. Yeah, I can see that. M, yeah. The center of mass, AC, yeah. Sam, okay, where is Sam? So Sam has a mass of 35 kilograms. Right, I don't know where Sam is sat. That's the problem. Tamsin has mass 25, okay, and sits at A. There we go. So I'm going to do something like that. 25, so 25g, because it's a force diagram. So what do we have left? Sam. Sam has a mass, but we don't know where Sam goes. Where must Sam sit for the plank to be horizontal? Give your answer as a distance from A. Okay, so from the left side. Well, before I draw it, I want you to think about where roughly Sam sits. Remember, the plank stays horizontal, we were told. Okay, hopefully after that, you see it needs to be somewhere over here. Yeah, I'm going to say somewhere like that. I don't know exactly where this is. Just a rough guide. So That will be 35g. Where must she sit? Well, it's helpful, if it's a distance from A, it's helpful to kind of draw that in and call the mystery distance x. And now the question is the same as before. Where can we do moments? Now, I know you want to do moments from the pivots if you followed before, but the quickest way is to do moments from A. Because when you find out x using moments from A, you answer the question straight away. So that's what we're going to do. So what have we got here? Anti-clockwise, anti-clockwise, clockwise. Okay, so moments from A. The 25g, oh no, we've got the reaction force as well, haven't we? Almost missed that. So we've got the reaction force. Okay, so if we did moments from A, so here's something that happens when you do moments from A. Because you're at that point, we talked about when you're really close to the point, the moment itself is almost nothing. If you take your moments at point A, you can effectively ignore this. The reason why you can ignore it is because you will be 0 away. It will be 0 times 25g. So that one is going to sort of disappear. What's the next force? The next force is the one that is 1.8 away. So 1.8 times 25g. Okay, what is that? That's a clockwise. From the point of A, that's clockwise. What's next? R. R is there, and R is anti-clockwise. Now, there's a problem. I don't actually know what R is. So is there anything else I can use? Remember, up equals down. So all of the forces that we drew down must be equal to R. So 25g plus 25g plus 35g, that's 85g, must be equal to R. So how far away is R? R is 2 meters away. So this will be 2 times R, and R is 85g. Okay, so that one you multiply by 0, so it sort of disappears. This one we've done, this one we've done. How about this one? Well, this is the one that is a mystery distance. So it's x times 35g. And you can probably see already that if I equate all of these to each other, I'm going to be able to solve the problem. Okay, and that's how we do that. So a couple of things going on here. Number one, getting a full diagram, being careful with not assuming that mass is in the center. When it's non-uniform, you have to draw it like that. If you know it says how far away is it from A, it makes sense to take your moments from A. This will save you some time. And the other thing is that property, again, is coming in useful, that forces up are equal to forces down. We've used that on this occasion to solve the problem. Could we have done it another way? Yes, we could have. We could have taken our moments at the pivot and called this distance here. I mean, what would that be? If this distance, well, you would just call this distance x. You could have done it, but you should still get the same answer either way. Okay. If you solve this one is equal to these two added together, you should get your answer. So let's take a look and see what they did. Yeah. So they've done moments about m. Okay, I wouldn't do it that way. You should still get the same answer as 3.57. Okay, you should get 3.57 if you have a go at it, as we talked about on the slide before. So that's it, really. That's the center of mass. Sometimes they tell you where the center is, sometimes they don't, so you just call it x. It's just adding another layer, really, to the problem-solving process, but it's very much the same.